Hey all, so welcome from a nice break on through Wednesday of trigonometry for your integrals. We are going to come back and we're just going to look at some partial fractions, which will hopefully feel much more sane after all that trig. So get yourself ready for notes, and we are going to talk about partial fractions. Now, partial fractions are a method that you're going to use when you see rational expressions like this. So where you have a numerator, denominator with polynomials, and certainly with things that you can factor. So we've talked a little bit about partial fractions when we were in pre-calculus, and I want to just remind you what this is coming from. And it's coming from this idea that when we add or subtract rational fractions, the denominator ends up being the product of the original denominator. So like if this is x plus 1 and let's say 3, and then this is x minus 2 and this is 5, then the new denominator is the product. Now in this case, the question we're looking at is, this would be much easier to deal with added terms. Right? It's easier to integrate, it's easier to differentiate added terms than it is a big fraction like this. Like there isn't a reverse quotient rule. And so what you're going to do is exactly that. You're going to look at this problem and ask yourself, okay, well, it's not going to be 3 and 5, but what numbers would it be so that we end up with this same result? So what you're going to do is you're going to say, well, what are my two fractions that would have given me x plus 5 over x squared plus x minus 2? Now, as you can see here, the first thing we want to do is factor, and those are going to be the denominators of our fractions. So in this case, that would be x plus 2, x minus 1. Those are the factors for this denominator. If there was a third one, we'd have that as well. And we don't know what the numerators are going to be, so we're just going to say A and B. Hopefully this feels a little bit familiar from our previous experiences together. Now all you're going to do is use a common denominator. So common denominator. In this case, I'm going to multiply by x minus 1, by x plus 2, and what's going to happen with the nice common denominator is that those all cancel out, and I'm left with this big equation of ax minus a, I'm doing a little distribution, plus bx plus 2b is equal to x plus 5. Now, if you remember from pre-calc, what we do at this point is we set up a system of equations where we have our x terms and our constant terms. So our x terms in this case are a and b on the left are equal to 1x on the right, and our constants are negative a plus 2b on the left and 5 on the right. So this is a system of equations that you can solve. The a's would cancel out, and we'd end up with 3b is equal to 6. So meaning that we now know that b is equal to 2. Substitute that in, a is negative 1. Now that took a little bit of time, but the idea of that is, okay, well this takes us from this very challenging integral here. A is negative 1 over x plus 2. I'm just going on this very crossed out work, but a over x plus 2 plus b, which is 2 over x minus 1, is the same as that big polynomial here, and now we can just integrate those. Now these are both the equivalent, these are very similar to blank over x. These are ln, so this would be negative 1 ln of x plus 2 plus 2 ln of x minus 1. Oh, those should be absolute value signs. I will fix that in a second as I erase this. Don't erase your notes. So then I end up with -1, or just negative ln absolute value x plus 2 plus 2 ln x minus 1 plus c, like so. So that's the nice thing with partial fractions. It just makes it a lot easier to integrate. Now, it's all, again, similar to our other substitution problems, is that, oh, I'm not sure why these numbers are off. The nice thing about it is you don't have to necessarily worry about substituting with a u substitution. You're just going to jump right in, and so when we have powers, when we have bounds, we say, oh, 9 minus x squared. That would be 3 minus x plus b over 3 plus x is equal to 1, because that's what it is when there's the dx. Like, this is the same as 1 dx here. So just those are equivalent. So you get used to that. 9 minus x squared. These are our factors. Common denominator is going to give us a times 3 plus x, a times 3 minus x. I'll let you do the algebra, but we end up with both a and b are equal to 1/6. So when we substitute that in, I'm just going to factor out a 1/6 and leave behind 1 over 3 minus x plus 1 over 3 plus x dx. Now when we integrate, that leaves us with 1/6 times negative ln of 3 minus x, like so, because the if we use u substitution, the du is -1, plus ln absolute value of 3 plus x, and these bounds then are going from -2 to 2, so this is why the absolute value is super important here. One thing that is also really helpful is remembering our rules for simplifying our logs. That can be really helpful here. Remember, if we have addition, this is multiplication, and here if we have subtraction, that's division. So in this case, I would even rewrite this as ln of 3 plus x minus ln of 3 minus x turns into the log of 3 plus x as the positive numerator, and so then that puts 3 minus x in the denominator, again from -2 to 2. So this simplification can be really helpful. So then I get 1/6, and this would be the ln of 5 over 1 minus the ln of 1 over 5, like so. This can be simplified even farther. So one thing that can be helpful to remember is that if I have a negative here with a log, it's an exponent, which means I can flip my fraction, just make it positive, just like we would if there was negative exponents inside of a fraction. So if I had like x to the -3rd over y to the -2, we switch it to positive exponents and it just flips the side of the fraction. Same thing happens with logs. So then I get 1/6 ln of 5 plus ln of 5. So that's 2 ln of 5s, which is 1/3 ln of 5. We could even call that the log of the cube root of 5, just in terms of like what might be in your multiple choice answers. Those are all equivalent, just remembering your log rules. Now, one thing that's important here in our last example, I'm not going to work the way all the way through this, but when you have powers on a factor in the denominator, when you're considering your options, just like before, you'd have a of x minus 1, b over x plus 1. You also have a third factor, which could be x minus 1 squared. So in this case, you need to include both of these options just by itself and as a duplicate. So this makes it a little bit harder to make a common denominator. So this a would need to be multiplied by x minus 1 and x plus 1, or x squared minus 1. B would be multiplied by x minus 1 squared, and C would be multiplied by x plus 1 to make the common denominator of x minus 1 squared times x plus 1, like so. So it's a little bit harder of a problem. If you're interested, I really would strongly encourage you to go through the steps as much as possible. I have a lot of them up on the PDF, but just like you'll have an x squared equation, you'll have x, and then you'll have constants, so that you have your 3 system equation for your 3 variables, a, b, and c. But it's just really important to remember that you need to include both the x minus 1 squared and the x minus 1 as options. Hopefully this brought back some memories of partial fractions. As always, please nominate anything you're stuck on in the form that's attached. Please send me an email, leave something in the comments, or set up a Zoom if you want to talk further. And I am here to help. Have a wonderful day.